Welcome back to the deep dive. Today we're going past the shiny interface, past the user experience, and we're dropping right into the engine room.
We are. We're going into the absolute foundation of the entire Sunmax LLC application.
I mean, it's the layer most people never see. You've got the tools, you've got the instant currency updates, but it's all built on something very specific.
It is, yeah.
Yeah.
A non-negotiable foundation. And that foundation is what the source material calls the Sunmax Bridgecode Architecture.
Right. And it's described as, well, much more than just code. It's the internal engine that's running everything, coordinating the tools, syncing the currencies, keeping the whole service humming.
Like a perfectly tuned machine. And our mission today really is to translate that, to turn this very technical concept into something that gives you real insight into speed and stability.
Exactly. If you've ever wondered why Sunmax feels so smooth, so fast, so alive, as they say.
Then this is where the answer is. It's the bridge code. We're basically going to dissect its heartbeat and show you how that experience is engineered from the ground up.
Okay, let's do it. So let's start at the highest level, the basic structure. The sources describe bridge code as a four-layer intelligence system. What are those layers? What do they actually do for the user?
Right, so each layer has a very specialized job. We start at the bottom with the core processing layer. Think of this as the front door.
The intake.
Exactly, the intake. Any raw instruction, a tap on the screen, a data feed coming in, it enters here. The layer's job is to immediately analyze it, format it, and compress it so it's ready for the next step.
So it's like a universal translator, getting everything into a standard language before anything else happens.
Perfectly put. Once it's formatted, it moves up to the execution matrix. Now, the matrix isn't just one thing. It's more like a grid of tiny, specialized microhandlers.
And their job is what?
Their mandate is very specific. Execute the operation with the least possible overhead.
Least possible overhead. Why is that specific phrase so important?
Because it translates directly to efficiency on your device.
Mm-hmm.
I mean, if a system uses less computational power for a simple request, two things happen. One, it saves battery life. Two, it guarantees performance. It prevents bottlenecks.
So the system can handle 10,000 requests just as smoothly as it handles one.
That's the goal. Efficiency drives that consistency.
Okay, that makes sense. But now we get to the part that I find fascinating, the intelligence layer. The adaptive memory nodes.
Ah, yeah. This is where that alive feeling really comes from.
Mm.
These nodes are not static. They keep a constantly updating map of your recent actions, your instruction patterns.
So they're not just reacting to what I do.
No, not at all. They're predicting. They're processing probability. So if you tend to check the gold rate right after you look at your portfolio,
Mm-hmm.
the moment you open your portfolio, the nodes have already started preloading the components for the gold rate view. The system is responding before you've even made the next tap.
It's one step ahead. It eliminates that decision lag you sometimes feel in other apps.
Fundamentally, yes.
And I have to ask, does that predictive model have benefits beyond just speed for the user? I'm thinking, like, on the business side, does it help manage server costs?
Oh, absolutely. By anticipating traffic patterns across all users, the architecture can allocate server resources much more intelligently. It scales things up and down precisely when needed, instead of just running everything at full power all the time. It's a huge cost saver.
Fascinating. Okay, and the fourth layer, the sync pulse layer. Why is timing so critical when everything is already moving this fast?
Timing is everything. It's the master clock, the conductor. You've got global currencies, live charts, UI tools, all running at once. They have to be perfectly synchronized down to the microsecond. Without that rhythmic pulse, you'd get drift, errors, instability. It's the glue.
So the big takeaway here is that bridge code isn't static code. It's dynamic, it's adapting, optimizing, and it's literally learning from you to restructure itself.
In real time, yes. It's built to evolve.
Okay, so we've got this structure, but how does information actually move between those layers? The Sunmax app has all these different modules, gold services, the tools panel, the 3.2 engine. They're like digital cities.
And bridge code is the high-speed railway connecting them. This is what's called module-to-module routing. When an instruction packet is ready, it uses a few key tools to get where it needs to go fast.
What are those tools?
Well, first, you have smart mapping. It's like the traffic controller. It's always looking for the clearest, fastest path to the destination module. Then, and this is crucial, you have priority channels.
So like an express lane.
Exactly. An express lane reserved for urgent requests. Think a trade execution or a critical security update. Things that absolutely cannot wait.
And what happens if a lane gets blocked? Say one module is suddenly under a heavy load and slows down.
That's where the safety net comes in, the failover relays. It's this unseen mechanism that's constantly monitoring for lag. If it detects a slowdown in one module, it instantly and automatically reroutes the packets through a different, faster path.
So the user never feels the hiccup.
Never. The system solves the problem before the lag can even register on your screen. It's designed to be self-healing.
That kind of dynamic routing has to have a serious brain behind it. Which brings us to LinkProtocol 7.8. This is the logic engine, right? The thing making all these decisions.
It is. LinkProtocol 7.8 is incredibly lean and fast. It operates on a really tight 5-step logic cycle that runs millions of times a second.
Let's walk through those 5 steps. What's happening inside that brain?
Okay, so step 1 is detect intent. It figures out what you or the system wants to do. Step 2 is where the speed really starts. Convert intent into compressed bridge code packets.
Compressed packets. What does that mean exactly? How are they compressed?
It's not like zipping a file.
Yeah.
It's more about stripping everything down. The instructions are converted into these super lean binary packets. They only contain the absolute essential data, the command and the destination. All the junk, all the extra headers, it's gone.
So you're sending a postcard with just the address and the message, not a big padded envelope.
That's a perfect analogy. The smaller the packet, the faster it travels. Step 3, the brain acts. Select the fastest possible route using all that live data from smart mapping.
Then step 4 is dispatching it.
Dispatch the packet.
Mm-hmm.
Right. And step 5 is the failsafe. Wait for an acknowledgement pulse.
A confirmation.
The confirmation that the job was done. If that pulse doesn't come back in time, LinkProtocol knows something is wrong, and it triggers a resend or a reroute using those failover relays we just talked about.
And what's amazing is that the source says this protocol is self-optimizing. It doesn't just find the fast route, it learns to find faster routes.
Yes. Every successful trip provides feedback. Over millions of cycles, it refines its own algorithms, shaving off tiny fractions of a second. It's that combination, the predictive nodes and the self-optimizing logic, that creates what feels like near-zero latency.
Okay, let's really dig into that speed, that famous Sunmax smooth experience. That's the rapid flow interaction layer, right? What is that layer actually handling that I would see every day?
Rapid flow is for everything that has to feel instantaneous. Smooth UI transitions when you swipe, currency conversions that happen the moment you type, the refresh rate on live charts. If it feels seamless, rapid flow is behind it.
And the source material has this one detail that just sounds, well, impossible. It says, rapid flow sends a pulse through bridge code before your finger even lifts from the screen.
It sounds like magic, but it's pure prediction. Remember those adaptive memory nodes?
Mm-hmm.
They've already calculated the most likely thing you're going to do. So the moment your finger makes physical contact with the glass, that tiny pressure is used as a pre-initiation signal.
So it's not waiting for the tap, the full action.
No, it's acting on the touch. It's leveraging those extra milliseconds by assuming your intent the second interaction begins. It's a tiny window of time, but when you add it up, it's the difference between feeling fast and feeling instant.
Okay, so speed is one thing, but speed is useless without stability. How does bridge code deliver on what the source calls pure, uninterrupted stability?
This is its other superpower. It's constantly performing maintenance on itself in real time. It runs these routine self-check pulses to make sure everything is okay. But more importantly, it uses something called instruction sniffing.
Sniffing for what?
It's sniffing for errors. It monitors every single instruction packet, looking for corrupted data, anything that looks wrong. If it finds an anomaly, it immediately triggers what's called dynamic correction.
What does that correction look like?
It's surgical. Doesn't shut anything down. It just isolates the one faulty micro-instruction and replaces it or reruns it on the fly. But the really wild part is instant micro-patching.
Tell me more about that.
Okay, so let's say a brand new, unexpected micro error, a tiny bug appears because of some weird combination of user actions. Bridge code can identify the source of that bug and automatically generate and apply a temporary patch right then and there.
So it's fixing bugs on a running system without me needing to download an update or restart the app. It's healing itself mid-flight.
That's it, exactly. While another app might crash, Bridge code is just quietly fixing these tiny issues as they happen. And what you experience is just stability, no crashes, no errors, even when the system is under heavy load.
This just highlights how important the smallest pieces are. Let's zoom in one last time, down to the tiniest units of intelligence. The microbridge instructions.
Right. These are the atoms of the system. Every single thing you do is broken down into these tiny commands. Things like fetch gold rate, switch theme, Render user data. That's the language Bridgecode speaks.
It must be an absolute nightmare managing millions of those every second. Who's the conductor for that orchestra?
That's the job of the dynamic handlers. Their role is absolutely essential for keeping the system intuitive and balanced. They're constantly juggling four main tasks.
And what are those for?
First, prioritizing instructions. Which tiny command needs to run first to keep everything feeling fast? Second, suppressing redundant instructions.
What does that mean?
Well, if you get impatient and tap a button 5 times really fast, the handlers make sure the system only executes the command once. It doesn't waste resources.
Okay. That prevents the system from bogging down.
Precisely. Third is intelligent workload distribution. They spread the work evenly across that execution matrix so no one part gets overwhelmed. And finally, just overall, maintaining system balance, making sure resources are always available for critical functions.
It really just proves that the intuitive, instant feel of the app isn't from one big, clever piece of code. It's from the perfect coordination of millions of tiny little operations.
The seamless experience is a byproduct of that computational harmony. It's proof that top performance comes from highly optimized micro-level intelligence, not just brute force.
So let's wrap this up. What does this deep dive mean for you, the learner? We've broken down the foundational structure, the core processing, the execution matrix, and those incredibly important adaptive memory nodes.
We looked at the brain, LinkProtocol 7.8, and how its self-optimizing logic and compressed packets deliver that high-speed routing.
And we uncovered the secrets behind that famous Sunmax experience, the near-zero latency from the rapid flow interaction layer, and the invisible safety net of real-time debugging and micropatching that gives it such stability.
Right. At the end of the day, understanding why the system feels so fast comes down to knowing this architecture. You now have the blueprint for that performance.
And this foundation is going to be so important for where we're going next. Our sources indicate the next deep dives will get into the practical applications, specifically the internal multi-currency engine and the 5 tools panel architecture.
Yeah, we'll definitely have to save those for another day. But before we go, let's leave you with one final thought to mull over based on what we've talked about today.
Go for it.
If these adaptive memory nodes are constantly anticipating your behavior, learning your intent, and literally restructuring the system around you, what level of a digital self is being created inside an application like this? And maybe more importantly, what should that mean for our expectations of all high-performance digital tools in the future? Something to think about.